So thank you for the introduction. I'm Shuyue from Columbia University. Today, I'm going to talk about the role of DNS in residential internet use. DNS is designed to direct users to the IP addresses hosting internet services. In this talk, we'll take a look at the role DNS plays in directing user traffic using proprietary traffic traces collected from residential buildings. It is well known how DNS works. However, when we look in the context of our residential traffic traces, we find that significant volume of traffic do not use DNS in the expected way. We know that services use DNS to direct the majority of user traffic, but we find that significant traffic volumes are not directed by DNS, as 12% of traffic cannot be paired with a DNS record. We also know that clouds and CDNs can update DNS records to redirect users, but we find that IP addresses from expired DNS records are prevalently used, as 13% of flows start after DNS records have expired. Besides, we also know that DNS query volumes can be used to understand service popularity. However, in fact, service popularity varies by metrics. Using traffic volume and the number of DNS queries can lead to quite different service popularity estimations. This talk is going to demonstrate these results about DNS in the context of our residential traffic. Before we go into details, first, let me introduce the foundation of all our analysis, our dataset. At Columbia University, most graduate students and faculty live in off-campus apartments that are owned by the university. We captured all traffic to and from 530 of these units. User traffic goes from user devices to an switch in the residential buildings. The traffic then goes through an aggregate switch to outside networks. The aggregate switch mirrors the traffic to a server in the lab, and the server records the traffic through a data collection pipeline. We collect traffic 4 times a day, every day for a month, and the average traffic data rate is 0.53 gigabits per second. Notice that our dataset is somewhat different from many campus datasets that researchers have access to, since we collect from residential users, while many campus datasets collect from dorms and offices. Our data collection pipeline protects privacy of users. At collection time, we first save some useful fields with careful attention to avoid including sensitive information. For example, for the domains, we only save the last 3 suffixes. We also anonymize privacy-sensitive fields in the header, such as MAC addresses and Columbia IP addresses. Then we discard the remaining payload. After we get the data, we post-process it by first aggregating packets into flows. A flow is defined as a group of packets with the same 5 tuple in IP header within an hour. The 5 tuple is transport protocol, source IP address, destination IP address, source port, and destination port. In order to identify the sites that users access, we pair flows with corresponding DNS domains. We know that DNS works this way. When a client tries to access a service, it will first send a DNS query for some domain to a DNS resolver. The DNS resolver will then return the server IP address to the client. After getting the server IP, the client will establish a connection between the server to access the service. Therefore, for a flow from a particular apartment, we look for the most recent A-record DNS query that's from the same apartment and that returns the result IP address, which is the destination of the flow. This method is also used in a paper in 2020. It's possible that a flow in our 1-hour capture is actually being directed by a DNS query before the hour, and either the record was cached or the flow started before the hour. For such flows, we look at DNS packets up to 5 hours before the hour capture and pick the most recent one with corresponding IP addresses. Using more than 5 hours didn't significantly increase the number of flows we could match. Our analysis concerns how users interact with internet services. Different domains may contribute to the same service. So based on the domains that flows pair with, we annotate flows with corresponding services. 12% of traffic in our dataset does not have paired DNS domains. 76% of traffic is mapped to 100 popular services using approximately 200 keywords from DNS domains. And here are two examples. In the examples, those domains are mapped to YouTube and Netflix services respectively. For the remaining 12% of traffic, we consider each domain as a unique service. And here's an example. In this example, this domain is used for public research university, City College of New York. After understanding the dataset, now let's take a look at traffic that cannot be paired with DNS records. We define those traffic that cannot be paired with a DNS domain as no DNS traffic. A paper in 2020 observed 7% of connections are no DNS, and it assumed that all of these no DNS connections are peer-to-peer. In our dataset, we saw like 27% of connections are no DNS, contributing 12% of traffic. And we believe there are three reasons behind no DNS traffic. The first reason is that some applications do not use DNS packets to direct users to servers. For example, some applications may be peer-to-peer. Some applications may adopt their own variants of DNS. For example, Tencent uses a self-designed protocol called HTTP DNS for services such as WeChat. In addition, some applications may hardcode IP addresses. Among those applications that do not direct users with DNS packets, we expect peer-to-peer applications to be the most prevalent ones. We try to identify peer-to-peer traffic with an inference technique. Our inference technique is based on three properties. First, peers tend not to be accessed through DNS. Second, peers tend to be in ISPs that host human users. And last, peers tend to use non-privileged, high-numbered ports. Our technique identified 6% of traffic, which is 17% of connection as peer-to-peer. Recall that the paper in 2020 saw 7% of no DNS connections, which serve as an upper bound for peer-to-peer connections. We see an increase from 7% to 17%, indicating a rebirth of peer-to-peer. This increase may reflect the growth of applications such as video conferencing apps and peer-assisted software updates. The second reason is the adoption of encrypted DNS protocols, such as DNS over HTTPS, DNS over TLS, and DNS over QUIC. But DNS resolvers of Columbia University do not support encrypted DNS, and our dataset includes very little traffic to popular public DNS resolver that is potentially encrypted DNS. So we believe that the second reason should only explain a very small amount of traffic. The third reason is that DNS records may be cached for a period longer than our collection window, or cached from DNS query issued on different networks. As we mentioned, using DNS packets more than 5 hours didn't significantly increase the number of flows we could match. So this also should only account for a small amount of traffic. In the next part of the talk, we will discuss the heavy use of IP addresses from expired DNS records. It is well known that many modern services are hosted in multiple locations. Content delivery networks and clouds use DNS to steer users. The ability to change the IP addresses for a service by returning a new record allows them to respond to failures, optimize performance, and load balance. But these changes can only be made when a new query is issued and the client uses the new IP address, not when a cached IP address is used. The use of IP addresses from expired DNS records can lead to limited resilience to failures. When a site fails, the CDN wants to quickly update to use a backup site. Let's see an example in this figure. In the beginning, the DNS resolver tells the client to use the server with IP address 2.2.2.2, but then the server fails. So now the updated DNS record tells the client to use the server with IP address 1.1.1.1, which is a backup site. But the client will only use the backup site when the cached record is evicted and a new record is received. DNS has a field called time to leave, TTL, indicating the time interval that a record may be cached before it should be discarded. And TTL violation means that the DNS record is cached longer than TTL. Even small TTL values cannot guarantee the use of up-to-date DNS records due to DNS TTL violations. Let's take a look at this diagram. This is when the client receives the record. This is when the DNS record becomes expired. And this is when the client evades the record from its cache. For example, here are 3 flows that start before the DNS record expires. And here are another 2 flows that start after the DNS record becomes expired. And those 2 flows violate TTL. In our dataset, 30% of flows start after DNS record expiration. Among those TTL violating flows, 50% of them start more than 56 seconds after the expiration. Notice that this staleness occurs before the recursive resolver, as we collect traffic at a point between clients and the recursive resolvers. This means that the problem is on the client side. Client caches can violate TTL and save records that should have expired. Besides, many client applications rely on the operating system to deal with DNS and will only receive the IP address, but not other information such as TTL. So it is up to the client application how long the IP address is cached and used. In addition, the use of IP addresses from expired DNS records can lead to limited agility to steer traffic. Clouds may update DNS records to use low latency paths. However, traffic may still go to IP addresses from expired DNS records. Let's look at this diagram again. Again, this is when the client receives the record. This is when the DNS record expires. And this is when the client evicts the record from cache. And again, we have like flows starting before the record expiration and starting after the record expiration. For flows starting after DNS record expiration, all the traffic is going to the destination IP address where the DNS record is no longer valid. In addition, even for flows starting before DNS record expiration, if flows last long, then some traffic also goes to the destination IP address where the DNS record is not valid. In our dataset, 50% of bytes originating from the residential buildings go to the destination IP address where the DNS record is invalid. This actually shows a limitation of using DNS to steer TCP traffic. To demonstrate that large volumes of traffic may use IP addresses from a DNS record well after its expiration, we plot this figure. The x-axis is the time between the DNS record expiration, and the y-axis is bytes that have yet to be sent. The blue line represents traffic sent to Microsoft. And this point shows that 80% of traffic to Microsoft is sent at least 5 minutes after the expiration. And the orange line is for Amazon, while the green line is for Google. And this point shows that more than 20% of traffic to Amazon or Google is sent at least a minute after the expiration. Again, this demonstrates a limitation of using DNS to steer TCP flows, as we cannot move the flows. Next week at SIGCOMM, we'll be presenting our work with Microsoft that solves this problem. This work painter can redirect ongoing flows to new paths and new destination IP addresses in response to failures and to improve performance. We also have another publication at IMC on better service redirection techniques. Please check them out if you are interested. In the last part of the talk, we will discuss the variability of service popularity when using different metrics. Researchers rely on lists of popular websites such as Cisco Umbrella Top List and SecRank List, which based on passive DNS usage. To understand if service popularities vary by metrics, we include 3 additional metrics. The number of flows, which represents how often users connect to a site. Flow duration, which represents how long users exchange traffic with the site. And last, the number of bytes, which represents traffic volume. And we plot this figure. The x-axis represents the top 1,000 services sorted by traffic volume, and the y-axis represents the percent of total DNS queries, flow duration, and bytes. Notice that the x-axis is on log scale. The blue line represents bytes. Orange line is for DNS queries. Green is for flow duration, and the red one is for flows. We can see that all measures identify the top services, such as YouTube and Netflix, as popular. However, they disagree on the importance of other services. For instance, applications such as Slack and Gmail, they generate a lot of flows and DNS queries, but little traffic. On the other hand, CrashPlan, a backup application for small business, generates a lot of traffic.
Excuse me?
And, yeah.
This is the timekeeper in the room. We have 5 minutes before Q&A.
Yeah, thank you.
Thank you.
Yeah, and CrashPlan generates much traffic but few flows and DNS queries. This shows that using different metrics may lead to quite different service popularity estimations. So we need to carefully consider what metric to use and use DNS datasets carefully. So in conclusion, in this talk, we showed the prevalent existence of no DNS traffic, aka traffic that cannot be paired with DNS records. In our dataset, 12% of connections are no DNS, and among them, 17 out of 27 are identified as peer-to-peer, indicating a reverse of peer-to-peer. This shows that rather than simply relying on DNS records, researchers need additional methods of mapping traffic to services in order to better understand internet service usage. We also showed the prevalent use of IP addresses from expired DNS records. 13% of connections in our dataset start after DNS record expiration, and 80% of traffic to Microsoft is sent at least 5 minutes after DNS record expiration. This demonstrates that we need better service redirection techniques. At last, we showed the variability of service popularity by different metrics. Using traffic volume and the number of DNS queries can lead to quite different service popularity estimations. This should suggest that we need to consider what the right metric is for a particular use case, and we also need richer data sets to estimate service popularity. At last, I would like to acknowledge the security, privacy, and networking teams of Columbia University's IT department and our collaborators from UCSB and Columbia for helping setting up the data collection. If you have any questions, please feel free to contact me through this email address. And thank you for listening. Any questions?
I will go on to the first question, and that is, have you seen a difference in behavior for IPv6 and IPv4?
Yeah, that's a very good question. The thing is, Columbia University does not support IPv6 for now, so that's why our analysis is mainly focused on IPv4.
Okay, second question from the room.
Ed Lewis, MyCan. For number 2, regarding use of addresses from expired records, did you consider that someone might open up a SSH terminal session and have it open for hours and hours? That they're not going to re-DNS, they're not going to look up the address of the host, they're going to keep using it over time. How would such a flow be accounted for in your experiment?
Yeah, that's a very good question. So let me actually go back to a slide. I think this should be the slide. Yeah, So as you can see, we do think there can be like ongoing flows that last for a very long time. So that's why we have like two measures. We kind of like first count like the number of flows that use that start after the DNS record expiration, and we also calculate the percentage of traffic that are sent after DNS record becomes expired. So I think there are like two different scenarios based on based on the use case. There could be like different service redirection techniques.
They can certainly be the same flow, but it may be a new packet. Yeah, so depends on your count.
Yeah, so that's why we mentioned this work. This work at SACOM. So I think this is not only a problem with DNS, but also a problem with TCP. Because once the TCP establish a flow, it's just going to be continued and like not interrupted. So that's why we have like this work painter that aims to be able to redirect like user traffic at any point to new paths and new destination IP addresses.
Yeah, because the reason why I'm picking up on this is that for a while there was concern about the fact that applications will not even know nor respect the TTL that DNS is working with. So that might be part of what's being counted or missed here, depending on how you just approach it.
Yeah. I think I heard the first part. So can you repeat the question? Is sorry. So is the question about the approach of the?
Yeah, to some extent was whether or not you were seeing that in your experiment, whether that was being, if it wasn't being noticed that this was happening, your expired traffic would be higher than you expect. It might be this expired traffic actually is a continuation of unexpired flows going on.
Yeah,
so, that's kind of what I was coming on.
Yeah, that's right. I agree with you. So for example, in this figure, we see that Microsoft has like more traffic sent up to expiration compared to Amazon and Google. So we are not like fully sure about the answer, but one of the factors we think that might be is the same reason you brought up. Like I think Microsoft is used a lot for enterprises that may have like VPN connections up all day long. So that's why they could have like very long flows, and that's why they may have like more traffic sent up to the DNS record becomes expired.
Okay, thanks.
Thank you.